Hello guys, today our group is presenting on the two engineering marvels, which is from Athens to AUTOCRAFT, the steel leaf springs, and the CFRP solar panel substrates. Let's start with a trip back to the early 19th century where the Industrial Revolution happens. Back then, traveling in a horse-drawn carriage was incredibly painful because every bump on the road went straight to the passengers. Hence, the leaf spring was invented by engineers to act as the first shock absorber by stacking layers of steel. It could be bent to absorb the heavy impact energy and make travel possible. As car evolved, we developed coil springs. These are the metal spirals you see in the most modern cars. They were invented for daily comfort because they are more flexible and react quickly to the small bumps. Moreover, we engineers also invent torsion bars to save space in compact cars, and air suspension for a luxury floating fuel. Instead of metal, they use thin rubber bags filled with air. This allows a vehicle to float over bumps and lower its height for easier passenger boardings, so it is most usually used in luxury cars and buses. But the leaf spring stayed. Because of its incredible strength, it remained the standard for high-duty pickup trucks and vans today. Now let's look at the star. In 1954, the first solar panel was invented in the Bell Labs because the battery died too fast in the heat, so they invented this. By the space race, after 4 years, satellites needed a skeleton to hold these panels that was light and won't rot in extreme space temperatures. So engineers create the CFRP solar panel substrate, which is a high-tech composite sandwich that is ultra-light to stay full and dimensionally stable, meaning that it stays perfectly flat while flying through the harsh vacuum of space. So this is how the Vega 1, the product of the space race of, from America, evolved into the modern satellite solar panel. To understand why a leaf spring bounces and why a satellite panel stays stiff, we must look at their chemical bonding. First, the metabolic bonding in metal leaf spring, where the C or delocalized electron is held by ions, ions, and interstitial carbon atoms. It is non-directional, so it doesn't care which way the atoms are pushed. This is why the leaf spring can bend and flex under a heavy trap without snapping, because the atoms simply slide past each other while the C keeps them held together. Second, the covalent bond and the van der Waals force in the CFRP satellite substrate. The covalent bond is the primary bond found inside the carbon fibers and the epoxy resin. It is directional and like a permanent rigid handshake between atoms. This makes the panel incredibly stiff and strong. It refuses to change the shape even in space like uh, critical environments. And second, the van der Waals force. While they are much weaker than the covalent bonds, they act as the interface glue that holds the carbon fibers layers to the polymer matrix. Without this, the panel would simply fall apart into the separate layers.
Today I will explain how different types of atomic bondings affect material properties such as strength, conductivity, and corrosion behavior using two functional components. Our group selected a steel car leaf spring and a composite solar panel structure. So now I'll talk about component 1, which is car leaf spring. The material is steel, application is suspension, bonding is metallic bonding. The steel leaf spring mainly experiences metallic bonding, which directly affects its mechanical, thermal, and chemical behavior. Effect of the bonding on steel properties: high toughness, good conductivity, corrosion risk. Metallic bonding gives steel high toughness and ductility, allowing it to absorb repeated road shocks without fracture. The presence of free electron allows efficient thermal and electrical conductivity, helping to dissipate heat during cyclic loading. However, this bonding also makes steel susceptible to oxidation, leading to rust when exposed to moisture and salt roads. For component 2, we have composite solar panel structure. The material used is CFRP, carbon fiber reinforced polymer. Application is for aerospace, bonding, covalent, and also van der Waals. The composite solar panel structure consists of carbon fiber and polymer matrix, where covalent bonding dominates within each phase, with weaker interfacial forces. So, the effect on bonding on composite properties, which are high strength and stiffness, electrical and thermal insulation, corrosion resistance. Strong covalent bonds in carbon fibers provide high tensile strength and stiffness, helping protect fragile solar cells from mechanical and thermal stress. The polymer matrix acts as an electrical and thermal insulator, preventing damage to sensitive components. Covalent bonding also makes the composite chemically inert, giving excellent resistance to corrosion and harsh space environments. But if you look down there, interfacial weaknesses, van der Waals effects. So actually, what you can see there is carbon fiber has strong covalent bonds, weak interference, van der Waals forces, then polymer matrix. You can see the type of bonding that is shown there. Like van der Waals forces at the fiber matrix interface are relatively weak. Under repeated temperature changes, this may lead to delamination, which can reduce structural integrity. So next, we have a simple comparison table. This comparison highlights how bonding influences different performance requirements in automotive and aerospace applications. So we're starting with the property of strength. In steel leaf spring, it is tough and ductile, while in composite solar panel, it is high stiffness. In conductivity property, steel leaf spring has high conductivity, while composite solar panel has low. Steel leaf spring is prone to corrosion, while composite solar panel is resistant to it. Steel leaf spring has rust fatigue as its failure, while composite solar panel has delamination. In conclusion, chemical bonding plays a key role in determining material performance. Metallic bonding suits impact-resistant automotive parts, while covalent bonding in composite provides lightweight strength and corrosion resistance for aerospace applications. As you can see there, this is like a summary where I have written bonding affects the properties, application, driven choice, and performance optimization. Thank you.
Hi, my name is Nur Afifah. Today I will be presenting about satellite solar panel substrate made from composite CFRP. It is focusing on its manufacturing advantages, disadvantages, and its sustainability impact. So, satellite solar panels require materials that are lightweight, strong, and stable under extreme space conditions, because one of the commonly used materials for this purpose is carbon fiber is reinforced polymer, or we call as CFRP. Okay, for the manufacturing advantages, CFRP is extreme lightweight, which significantly reduces the overall mass of the satellite. This leads to lower fuel consumption during launch and ultimately reduce launch costs. In addition, CFRP has excellent resistance to UV radiation, space radiation, and vacuum conditions, which is allowed the material to perform well in harsh space environments and ensures long-term durability of the solar panel structure. Another key advantage is its low coefficient of thermal expansion, because CFRP expands and contracts very little when exposed to temperature changes. This provides good dimensional stability during thermocycling. It is preventing warping or misalignment, as the satellite moves between hot and cold regions in the orbit. For this, despite these advantages, CFRP also has several manufacturing disadvantages, which is one major disadvantage is its high cost, because the material itself, which is carbon fibers, are expensive, and the manufacturing process often requires autoclave curing, which involves high pressure and high temperature, increasing production and operational costs. Furthermore, carbon fiber production is energy intensive. The fiber manufacturing process requires very high temperature during carbonization, making it less environmentally friendly. Lastly, CFRP has anisotropic properties, meaning that its mechanical performance depends heavily on fiber orientation. If the fibers are not properly aligned during layup, the performance can be compromised, which increases manufacturing complexity and requires skilled workmanship. Moving on to the sustainability impact, the lightweight design of CFRP improves mission efficiency by reducing the overall mass of the satellite. Less fuel is required during launch, which contributes to better energy efficiency throughout the mission. However, despite its lightweight advantage, CFRP production involves high energy and material usage. This contributes to a higher carbon footprint during manufacturing. In addition, CFRP has poor recyclability compared to metallic substrate. Unlike metals, CFRP is difficult to recycle at the end of its life cycle, making waste management a challenge and reducing its overall sustainability performance. In conclusion, CFRP is an excellent material for satellite solar panel substrate due to its lightweight, durability, and thermal stability. However, its high cost, energy-intensive production, and recyclability issues must be carefully considered when evaluating its sustainability. Thank you for listening.
So let's start with manufacturing consideration of steel leaf springs. On this slide, you can see the advantages on the left side. Steel is suitable for mass automotive production because it can be manufactured efficiently and consistently, making it ideal for large-scale production. Steel also can be formed using rolling and heat treatment processes. This allows manufacturers to create leaf springs with precise mechanical properties, such as the right flexibility and strength for carrying heavy loads. Another advantage is durability. Steel leaf spring can withstand repeated loading over time, which is essential for vehicles that carry heavy cargo or travel over rough terrain. And finally, steel is more cost-effective compared to advanced composite materials, which make it a preferred choices in the most commercial vehicles. Now, looking at the disadvantages on the right, one of the main drawbacks is weight. Steel is dense, so leaf springs made from steel add significant weight to the vehicle, which can impact fuel efficiency. They are also prone to corrosion, so protective coatings or surface treatments are necessary. Lastly, producing steel energy is intensive, which contributes to environmental concerns. An optional real-world example is, for example, trucks, SUVs, and commercial vehicles often use steel leaf springs because their durability and load-bearing capability outweigh the disadvantage of weight. Next, moving on to sustainability. Steel is highly recyclable. so it can be reused multiple times without losing its mechanical properties. This reduces the needs for the raw material extraction, which in turn helps conserve natural resources like iron ore. However, producing steel is an energy intensive process, and it contributes significantly to carbon emission. This is an important consideration when evaluating the overall environment impact of vehicle components. Another factor is weight. Heavier steel components increase vehicle fuel consumption, which indirectly adds to carbon emissions during the vehicle's lifetime. Even so, recycling old steel leaf spring from commercial vehicles helps reduce their environmental footprint. So, while steel leaf springs have clear sustainability benefits due to recyclability, there are still challenges related to production energy and fuel efficiency.
To conclude, both steel and CFRP composites are selected based on how their bonding mechanisms and material properties match their specific applications. For the car leaf spring made of steel, the presence of metallic bonding, often described as a sea of Dirichlet electrons, which allows the material to deform plastically without fracture. This gives steel a high toughness and ductility, enabling it to absorb large impact energy repeatedly, which is also essential for handling road shocks. In addition, steel offers high strength, good fatigue resistance, and lower cost, and also high recyclability, which is making it suitable for mass automotive production. However, its high density susceptibility to corrosion and energy intensive production increase fuel consumption and environmental impact. On the other hand, the satellite solar panel substrate uses CFRP composites, where strong covalent bonds in carbon fibers provide exceptional tensile strength and stiffness, while the polymer matrix offers thermal and electrical insulation and chemical resistance. These properties help protect fragile and solar cells from damage during extreme temperature changes in space. CFRP is also extremely lightweight, which has a high stiffness to weight ratio and a low coefficient of thermal expansion, which is to ensure dimensional stability and accurate solar panel alignment in orbit. However, CFRP has limitations such as high manufacturing costs, energy-intensive fiber production, and poor recyclability and susceptibility to delamination due to weak van der Waals forces between layers. In summary, steel is ideal for terrestrial applications like car leaf springs, where toughness, durability, and cost efficiency are critical, while CFRP is better suited for space applications where lightweight design, thermal stability, and performance under extreme conditions are more important despite sustainability challenges. Thank you.